Welcome to numerical ship and offshore hydrodynamics. Today is the lecture 27. Today we are going to discuss some basic idea about the free surface Green's function. A very rough idea, we are not going to go into detail, like we will just discuss that how I can get the free surface Green's or integration of the free surface Green's function. However, which is more interesting part later on the second phase, I am going to show you that how actually you write a not write, like use a commercial code which is WAMIT. Now, this is the keyword that you have to use to get this lecture. Okay. And this is the reference that the discussion I am going to give for this free surface Green's function, that the thing you can get from this reference. Okay. Now, as you know, this is the expression for the free surface Green's function. We have discussed it is very complex. There are many reasons. The first thing is that it is a improper integral, because you have this integration limit 0 to infinity. So, this is the one, and also you can have a Bessel function here, which itself is a infinite series. So, therefore, we have a integral equation, improper integral equation together with a Bessel function, which is again a infinite function. So, it is the solution is not easy. Okay. Now, also we have the Rankine source at the beginning. Now, we understand that how to deal with the Rankine source. We discuss a lot about how we can deal with the Rankine source. Now, let us today how to deal with this the free surface Green's function. So, there are many literature available. Mostly there are many approaches one can take. Now, somebody can do the direct integration technique. What they do is as follows. Suppose I have a panel something like this, and already we know that how to discretize it and you get these panels. Now, over this panel they can use this is direct Gaussian quadrature rule they apply, and they get the value for this integral. Okay. So, it is called a direct numerical approach. So, you see that here the main issue is the convergent, and as well as the Bessel functions, you have to have a some infinite series you have to deal with. So, this is one way of going into this. However, in fact, if you look at the work by several researchers, people use this. It is not that nobody uses the direct numerical integration technique, but they are very popular to use some kind of asymptotic solution, some kind of series solution to get this value, integral value for this Green's function. Now, what is asymptotic solution or what is the series solution, those things are very core mathematical thing, and then I really do not want to discuss here in this course. But however, to give some kind of flavor, let me explain that how to integrate using those functions. Okay. Now, here actually if you look at this expression, this Green's function here, before I go into solution, I have to define so many things. Now, here this R, this from this expression you can understand is it is nothing but the projection in the horizontal z equal to horizontal z plane. So, it means that if I have a so this is the thing, if I have any source point here and then you have any field point over here. So, then see this distance is nothing but your R. Okay. Now, if this is the sea bottom and this is the source point, then this R 2 is basically the image about that depth, which is the seabed. Okay. And here this nu is nothing but the solution for the deep water dispersion relation. Now, what is the deep water dispersion relation? It is omega square equal to g k. So, just nu is nothing but it is omega square by g, which is the deep water solution. And then what is the mu? Now, here you say like mu is the solution for the this dispersion relation. Now, here there is a very deep mathematical things involved here to explain this what is mu. Now, the dispersion relation is nothing but omega square equal to g into k into tan hyperbolic k h, right. So, this is the, and then from this you can get, if you take omega tending to infinity, then you get the value for nu. However, suppose if you want to, now here it is we have to looking into the solution, and now it is a infinite improper integral, the limiting value is 0 to infinity, and how to solve it? It only can be solved with the help of some infinite series. Now, to get this infinite series, I need infinite roots. So, how I get this infinite roots? So, I just change this k into I k. If I do that, then actually I can have another set of integral equation, another set of dispersion relation, just changing k into I k, and now you can have the infinite solution or infinite root for that particular dispersion relation. So, details you can take any standard book, water is mechanics book, try to get what is called the evanescent mode and how to use this evanescent mode. So, here we really do not want to go into that deep into mathematics, but at the end you need to know what is what. So, for that this mu is nothing but the root of the dispersion relation if you replace k by I k, then you can check it out what equation you will get. So, solution for that is nothing, the root for that equation is nothing but your mu. Okay. And then now you understand that mu has that infinite number of solution. Okay. Now, here you can see that is the idea. Now, what you can do is, what we do basically we separate this integration zone into several zone based on the ratio between this r by h. So, this is nothing but this ratio between r is basically what is the projective distance divided by the water depth. Based on that we actually write several solution. Okay. And these are all available for last 30 years, these all are available. Now, if this r by h is greater than 0.5, okay. So, it means that when the source point and the sink point is really have a very large distance, right. So, and then if you, and h is the finite depth. So, h may not be that large. So, in that situation you can have this one, right. Now, here you can, as I said, you can solve this by infinite series. Now, you can see in this infinite series you have this mu m. Now, you realize that why I discussed so many so many things about this root of this dispersion relation. So, now you understand that you required those evanescent mode, those solution of this dispersion relation and changing this k is equal to I k, right. You then you have this infinite number of solutions, and these are the root of those solutions. You have to use this root to get the value for the g. So, this is the region 1. Now, in the region 2, now I just very briefly I just write all other regions. So, in region 2, here it converges very quick if 0 point, I mean this r by h greater than 0.5, but in this region when this r by h lies between 0.05 to 0.5. So, that means when it is little bit closer, it is that means that source point and the field point, it is little bit closer, right. So, in that situation you need more number of terms. For example, if you need to take here, let us take let us say some 10-15 terms to get the convergence solution. Maybe in this situation you need to take some 30-40 term to get the convergence solution, right. Now, if it is really close, right, then we are going to use some another type of series, and here you can see there is a another type of Bessel function also comes into picture, right. And also if it is very close, then also you have some another type of series function. So, we have to use this sort of series to get the solution for the free surface Green's function. Okay. So, I think this is enough for now, because this is not the idea about that how to write a numerical code for such complex thing. We are okay with having some basic idea, basic coding rule, basic coding structure. Okay, we are okay with this. So, this requires some more effort, maybe later on we can go through some literature and you can find out how to get the solution for this one. Okay. And always if you do not use all these things, you can simply use the direct numerical integration technique. Okay. I mean that plain Gauss quadrature rule, you have this panel. So, you take this Gauss point and then you are using directly this function and you can do the integration. Okay. So, this is the end. Nowadays you have the MATLAB, you have the Python. In this MATLAB Python, actually integration of such free surface Green's function is really not that difficult. Okay. So, you can use this these values directly into your MATLAB solver and you can get the value for the G. Okay. So, now let us stop on this particular discussion. Now, in this next phase, let us try to see that how actually we can use a software and how I get the result using some commercially available software, which is now we are discussing about one popular software is WAMIT. Okay. So, now let us see that how to use this WAMIT to get the motion of the body. So, now first actually to run any software you need two things, like how to input and then how to understand the output. So, now if you see the WAMIT, it has there are some 5 files you have to deal with. Now, first one is the geometry file. Now, this is something is a paneling. Okay. So, it is nothing but you have a geometry and then this file only take the meshing. So, this file is for the meshing purpose. Now, if you have rhinoceros software, then you can directly get the GDF file, otherwise you have to make this GDF file manually. So, how to make this GDF file manually, we are going to show you. Next one is called the pot file, or you can say the potential file. In this potential file, we need to input all these wave parameters. Okay. And then you have this FRC file, FRC stands for the force file. Okay. So, in this FRC file, we have to input all this parameter that is used to solve the equation of motion. That means, you need to put that radius of gyration, the mass matrix, etc. And then also this CFG file that configure your CPU, RAM, etc. Okay. And finally, now we have to understand that when this WAMIT is started in 1980, I think late 80, maybe 1986 onwards, that time people used to use the Fortran. So, in this Fortran they do not have that kind of fancy thing, right. Nowadays that is available in your MATLAB, or not MATLAB, sorry, in any CFD based software like ANSYS or another thing. Like you have a mouse, you click, you open the file, you go to the file and you run it. So, those things actually is not available in WAMIT. What actually here they required is they want a folder, like they want a path where you are keeping all these files. So, that is actually in a that fnames.wam file. Now, if you are doing little bit of coding using Fortran or if you are experienced coding in C# or you are doing some console application, if you do something called the console application, if you do that, then actually you have some file called exe folder, right. In this exe folder you have that compilation file, and it is basically named as some start.exe kind of thing is now. Now, in this folder when you click this code to run, so first actually it go to this location where this exe folder is there, and he reads everything inside this exe folder. Okay. So, now here if you use, so if you put this file, this fname in this exe folder, so under this folder he will know that what is the path of these files and what is the name of these files. Right. Nowadays, what actually what we are doing using this user that GUI, like graphical user input, right. We use this graphical user input we call GUI. So, using GUI what we do, we actually specify the location of all these files, right. But in that time it is not available. So, what is happening, this all the thing they kept into the exe folder, right. So, this is very important. If you do not put this, then your WAMIT will not run. Okay. So, now let us see that how this all the file looks like. Now, suppose you do not have the rhinoceros and you need to create the GDF file .gdf, then how you can create it? You can use a notepad to do that. Now, what you need to do is that you need to remember this is the format of the GDF file. So, first thing is nothing but that ulen, because WAMIT give all the result in non-dimensional form. Okay. So, therefore, sometimes let us say that as you know that the force is nothing but the mass into acceleration. So, it is m into L into t to the power minus 2 in this is it. So, then in order to get the force you need to divide it some mass into acceleration form, right. So, when you non-dimensionalize this force, then at that time we are going to use this ulen basically, right. Now, you see that its mass is nothing but the dimension of L cube, right, is and multiply, of course, multiply by the rho, right. So, therefore, normally if you look at the output, all the forces that WAMIT provides in a non-dimensional form. So, that time we require this ulen, because normally they divided with the L cube for the force, I mean that like and the moment L to the power 5 something like this. So, here normally we can take it 1, sometimes people use the length of the vessel. So, they take like 100 the length of the ship. So, then put a ulen equal to 100, it is up to you. Second one is nothing but the gravitation, the g, acceleration due to gravity. Okay. And then this term is actually it is the geometric symmetricity. Now, if your ship normally, that is what is happening, it has port starboard symmetry, right. And suppose sometimes if your ship is symmetric in all direction, for example, your ship is like this. So, this is symmetric about this axis, it is symmetric about that axis. So, if it is so, we put both are 1. but if it is not symmetric, then we are going to put at 0. So, when I put it is 0, it means that I am not using any symmetricity property of the input file. Okay. So, in that case what we need to do is, if you put 0 0, then you need to mesh the whole ship, you cannot mesh the half ship. Okay. So, because we are not using the symmetricity, right. So, 0 means we are not using any symmetricity. So, we need to give the mesh of the whole body. However, if you use the symmetricity, then you can use the 1 and you can use like you can put the half, let us say if it is about this and not this. So, this about this axis you can put 1 and then other value you can put this value is 1 and you can keep the other value as 0. And if it is symmetric in all the end, then you only need to give the 1/4 of the geometry and then you can define both as 1. So, if you use the one symmetry, then use one I s x equal to 1 and then I s y equal to 0 or otherwise. And if you use the 1/4, for example, you try to find the hemisphere. So, it is a circle. Circle is a complete symmetry is all everywhere. So, you can just take 1/4 of the circle and then you can use both symmetricity 1 and 1. So, this is the idea about the file. And one more important thing, like this is not the end, you have to know how to give this value. If you are getting it from rhinoceros, fine, otherwise how to give this. Here you can, if you look at carefully this first 4 thing, this first 4 actually define the first panel. So, now if it is a quadrilateral panel, so in that case you have to use the 4 corner. So, that is how you have to give the input. Now, you can ask me then what sir, what is going to happen, like if this is another panel. So, this is coming twice, it is defined for this panel and the same point defined for this same panel also, right. So, you have to mention in that case 2 times. So, let us make it point P 1, let us take P 2, it is P 3 and P 4, let us say it is P 5 and P 6. Then your input file should be first the value for P 1, the first row. So, P 1 x y z, then it is P 2 x y z, then P 3 x y z and then P 4 x y z, and again you have to say for the second panel P 2 x y z, okay, and then P 3 x y z and so on, right, and then it is P 5 and then it is P 6. So, this is, so that means that you need to repeat it is that many times it is coming, that many times you have to repeat the whole thing. That is how you need to create your GDF file. Okay. So, now this is the potential file. If you look at it, so it is the name of the potential file, and here it is you have the so now how you can write the pot file. Now, you can see here I have age POT and X body 1 to 4. Now, the first define the water depth. So, now it is given just a dummy value, it is given -1 and X body is nothing but the angle of the body. I mean, if it has a trim or heel, initial trim and heel, then we need to mention this all these 4 values. So, normally we do not do that. So, we just keep it as 0 and then this I rad and then I diff is basically it is asking for your radiational and diffraction potential. Sometimes suppose actually in that case actually I am making all the modes on. Let us see the I mode is nothing but that the mode of motion. So, the first one for the surge, the second one is for the sway, third one for heave, then roll, pitch and yaw. So, I am making everything on here, just dummy case. Now, sometimes I can make only, let us say this way. So, I am doing that surge, then heave and pitch, I just interest upon these three, and then if I make this I rad this equal to 0, then it only calculate these 3 mode and does not calculate these 3 mode. And if I make I rad equal to 1, so even if I do not need these 3 mode, but still it can calculate the radiation diffraction force in all 6 mode. And if I make it -1, they do not consider there is a radiation. Similarly, for this diffraction force also, if I make I mean this term, this I d I f f, I diffraction, if I make this equal to 0, then it can only consider this 1, 3 and 5 mode, these 3 diffraction mode. And if you make this equals to 1, then though I do not want the in second, fourth and sixth mode, still it will calculate all 6 mode, right. And if I make it -1, then it assume that there is no diffraction. Okay. So, this is the format of the pot file, and this is the format of the FRC file. Now, it is actually you can see that one important thing is basically here this IOPTN, this I option file, you can see is called the option file. Okay. And this is the this is the row you can define over here, and you have to finding out that the location, the CG location of the body, and this is the mass matrix, right. Here I can see I can only consider this linear, I mean this 1, 2, 3, the only that angular moment I just make it 0. So, I am not interested, right. Here I just interest as I say 1, 2 and 3 in that way. So, I just give the mass matrix. It is a dummy file, if you want you can give the other values also. Here you can take IXS, IXS and IZZ value also is the input. Okay. Now, the interesting thing is the options file. So, what is the option? That it is actually used for your output. What output you actually want from the WAMIT. Now, if you want the added mass and damping, so I want it, so I make it 1. If I want the exciting force from the Haskin relation, I make the option 1. If I want from the this panel method code, diffraction potential, exciting force from diffraction potential, I make this option 3 1. And if I know this motion also, so normally we want these 4 only, right. I am interested on to get the added mass, I am interested to get the exciting force, I am interested to get the motion of the body. However, for the detailed analysis sometimes it is important, there are different altogether there are what I said that scenario, like when you look at the second order forces, sometimes we are interested, sometimes actually suppose I have a body with a moon pool, let us say. So, at that time actually I am interested to finding out that what is the pressure field around the body. So, sometimes let us say there are 2 body side by side. So, if you want to find out what is that in between fluid, what is the resonating situation. So, at that time you need the hydrodynamic pressure on the body, you want to know the hydrodynamic pressure on the surface, all. So, those are the special situation when you need all this information also. Otherwise, normally we are going to use this for standard thing, right. So, this is about this FRC file, and this is how we configure the computer. Okay. So, just you can follow the WAMIT manual, it is written over here, how to set your RAM, how to set your all other things. So, this is over here, you can control that to this CFG file. Now, finally, let us see that how I can get the output file. If you remember that here I talked about the option file, Now, here if you click option 1, now then this is how actually you can get your this way you can get your added mass and damping. Now, you see like the first this file should be written in this way, the first one is period, then the modes and then the term Aij and Bij in that way. Now, let us see that this is basically your added mass file. Now, if you look at here, these are the time periods. So, these are the time periods, right. Now, the second one is the mode. So, that means this is the added mass for A 1 1. So, mode 1 mode 1. For example, now this one if I just mark these values, this one is the added mass for 3 3. So, this is the added mass for 3 and this is the damping coefficient, right. So, this is how actually I can read the option 1 file. If you make it on, then you get this result. Now, let us see that if you want the option 2, then what you get. Now, if you just look at here, the option 2 is the exciting force, option 2 and 3 both are the exciting force, one is from Haskin relation, one is for the differential, both are almost the same. Now, here how it actually you can see. Now, it is I is nothing but the mode that I am interested in, then the next column is the modulus of the amplitude and next the phase and then the real part and the imaginary part. Now, if you look at this format, now you see here this is the time, right, and then the next one is the heading angle, the beta. Now, you can see the heading angle is 180 degree. Now, here it is the mode. So, that means I am talking about the exciting force F 1. Now, if I look at here, it is the exciting force for F 3, okay, F 3. Now, the first one is nothing but the modulus of the force, this is the magnitude. Now, this one is the phase and this is the real part and this is the imaginary part. So, actually you really do not need the last two, right. Now, from this last you can verify whether this one is correct or not. From the imaginary real part, if you take this square root of a square plus b square, then you get this the magnitude, and if you take tan inverse b by a, you can get the phase. Okay. Now, this is the motion. Now, if you look at that how the motion gives here option 4. Similarly, first is the period, then the heading angle, then the mode you are interested, and again the magnitude and the phase, and also since it is a you find out in the complex potential, normally you get the complex number. So, it will give you the real and imaginary part. You see here, now this is the mode 3, I am just striking this is the mode 3. So, this is the for the heave, right. So, first one is the frequency time period, second one is the heading angle. So, it is beta, and this is the mode. Now, I am choosing the mode 3 and this is the magnitude. So, mod of xi 3, and this one is the phase. So, it is epsilon 3, and this one actually you do not need, is the real and imaginary part. Okay. So, you can see, so now in WAMIT you can see that you can have all kind of information. You can have the added mass damping value, you can have the diffraction force, you can have the exciting force, also you can have the motions, right. So, this is how actually you can get the put the input to the WAMIT and also you get the output from the WAMIT. Now, you know that how important this is, because based on that actually we are going to have the solution for the impulse response function based method that we are going to discuss from the next class. Okay? Thank you.